Hello everyone, I am Dr. Sirajul Afasi. I welcome you in my YouTube channel. Today in this video, I am going to talk about asymmetric synthesis. You know the process in which an asymmetric compound is synthesized from a symmetric compound to yield the positive and negative isomer directly is termed asymmetric synthesis, or the process in which a chiral compound is synthesized from an achiral compound to yield the positive or negative isomer directly. So, we have already seen that when a compound containing the asymmetric carbon atom is synthesized by ordinary laboratory methods from a symmetric compound, you also know the product is a racemic mixture. You know the concept of racemic mixture. If such a synthesis is carried out under asymmetric influence of a suitable optically active reagent, one of the optically active isomers is produced in preference and in excess. When pyruvic acid is reduced as such, it yields lactic acid. However, when pyruvic acid is first combined with an optically active alcohol, such as menthol, to form a ester, which is then reduced, the product upon hydrolysis yield minus lactic acid in excess. So see the scheme: menthol, it gave methyl pyruvate, and then further reaction with, you will get the minus lactic acid excess and plus lactic acid and menthol removed from. So in nature, numerous optically active substances such as terpenes, alkaloids, pyrotenes are produced by asymmetric synthesis under the influence of optically active enzyme. And these enzymes unite with the substance available in plants, and when the synthesis is complete, they separate from the product and are thus again free to combine with the more or parent inactive substance, and the endless process continues. So you can see the pyruvic acid have the nickel and H2 hydrogenations. You will get the minus lactic acid and plus lactic acid, and this is the minus lactic acid in presence of yeast. So we have the two pathway with the chemical and with the biological process like yeast. Now Walden inversion. When an atom or group directly linked to the chiral carbon atom is replaced, the reaction may proceed with the inversion of configuration. That is the important here, inversion of configuration. And this phenomenon was first observed by Walden in 1895, and hence the name Walden inversions may also be defined as the conversion of positive form to negative form or vice versa. Thus malic acid may be converted to minus malic acid. You can see here Walden inversion is the inversion of a chiral center in a molecule, not other center, in a chemical reaction, since the molecules can form two enantiomers around a chiral center. The Walden inversion converts the configuration of the molecule from one enantiomer form to the other. So malic acid, which is positive configuration, may be converted to negative malic acid as follows. So this is the formula and structure of malic acid, which contains two C double bond OH groups and one hydroxy group. It reacts with phosphorus pentachloride in presence of base. This hydrogen, this OH group is replaced with the chlorine, and further reaction with the silver hydroxide, it gives malic acid. So starting compound configuration and the last compound configuration is different. Since SN2 reaction always proceed with inversion of configuration, Walden inversion is a type of SN2 reaction. Look at here, this is the chlorosuccinic acid. When OH minus approaching from backside, it comes with the transition state, and after removing Cl minus, it gives malic acid. So now Fissure projection, that is also very important, how to write in Fissure projection of your molecules. When we attempt to depict the configuration, we face the problem of representing three-dimensional structure on a two-dimensional surface. So to overcome this difficulty, we use so-called Fissure projection. It is the most convenient way of viewing molecules with more than one chiral center. Fissure projection is a convenient 2D drawing that represents a 3D molecules. To make a Fissure projection, you view a chiral center so that two substituents are coming out of the plane at you, and two substituents are going back into the plane. Then the chiral center becomes a cross on the Fissure projection, and every cross in Fissure projection is a chiral center. So look at here, we are writing here, but how this one is converted into this form. So here these two is normal, then you convert into W and X in different way, and this is the your W, X and Z and Y. And this is the structure of a symmetric carbon atom drawn in a prescribed orientation and then projected into a planar surface. So planar formula of the asymmetric carbon are obtained by placing it so that two substituents are horizontal and project out towards the viewer, shown by the thick wedge-like bond, while the two other substituents are vertical and project away from the viewer, shown by the dotted line. So remember, in Fissure projection, molecule is oriented so that the vertical bond at chirality center are directed away from you and horizontal are directed towards you. So planar representation of the two form of the lactic acid may be given. So look at here. In this formula, the horizontal bond, that is COH and CH, project towards us out of the plane of the paper, whereas vertical bond C double bond OH and CCH3 project away from it. So inspection of the model shows that one interchange of a pair of substituents invert the configuration, changes one enantiomers into its minor image, whereas an even number of such interchanges does not. Thus, interchanging of H4OH in one gives the enantiomer second, while the interchange of CH3 for COOH and H4OH leave the configuration unchanged. So, you can see how you will convert this form to this form. This is the OH and this is the H and this CH3 and COOH. So, this is the projections. Projection means if you molecules have, then you now assign configuration to chiral molecule. Absolute and relative configuration. Actual 3D arrangement of a groups in a chiral molecule is called absolute configuration. While discussing optical isomerism, we must distinguish between relative and absolute configuration. You know the arrangement of atom or group about the asymmetric carbon atom. Let us consider a pair of enantiomers, say positive and negative lactic acid. So this is the structure of lactic acid, and this is the clockwise, that why it is positive, and it is a negative lactic acid anti-clockwise direction. So we know that they differ from one another in the direction in which they rotate the plane polarized lights. In other words, we know their relative configuration in the sense that one is the opposite configuration to other, but we have no knowledge of the absolute configuration of the either isomers. What is the absolute configuration? And that is, we cannot tell us to which of the two possible configuration correspond to plus lactic acid and which is to the negative. Then we know the RS system. The actual three-dimensional arrangement of group in a chiral molecule is called absolute configuration. We know specify the configuration by using RS system, and this is newer and more systematic method of specifying absolute configuration to optically active compound, since it has been proposed by RS Kahn, C.K. Ingold and B. Pirilog. These are three scientists, therefore known as Kahn-Ingold-Pirilog system. In simple, we say CIP rules. And this system of designing configuration has been used to increasingly since the early 1960s may eventually replace the DL system. So in this system, 4 groups attached to the chiral carbon are arranged in decreasing order of priority 1, 2, 3, 4 by applying priority rules. We then view the chiral carbon with the lowest priority group on the side opposite to the observers. So you can see A, B, C, D, which one is 1, 2 and 3, you have to design according to this rule. In the above example, A has the highest priority followed by the B and C, and while D has the lowest priority. So if the I while moving from 1 to 3 travel in a clockwise or right hand direction, the configuration is designed R Latin rectus means right. So this is the wheel, right turn means R, clockwise as seen by the observer, and this is the priority order. So if the I while moving from 1 to 3 travel in a counterclockwise or left hand directions, the configuration is designated S Latin sinister means left. So rule number 1, look at the 4 atoms directly attached to the chirality center, and that is your target, and rank them accordingly to atomic number. So the atom with the highest atomic number has the highest ranking first, and the atom with the lowest atomic number, usually hydrogen, has the lowest ranking means fourth. So this is the priority 53, highest priority, bromine 35, chlorine 17, SH, thiol 16, OH hydroxy 8, NH2 7, CH3 16, and hydrogen is the lowest priority. So now rule second, for isotopes, the higher the atomic mass, the higher the priority. For example, deuterium hydrogen 2 has the higher priority than protium hydrogen 1. So this is the lowest priority order and this is the highest priority order. So if you go through the rule 3, if a decision cannot be reached by the ranking the first atom in the substituent, look at the second or third or fourth atoms away from the chirality center until the first difference is found. So highest CH2Cl, CH2OH, CH2NH2, CH2CH3, CH2D and CH2H. So this is now we are moving to away from the chiral carbon, means nearby carbon. Now rule 4th, multiple bonded atoms are equivalent to the same number of single bond atoms. So priority sequence of common groups and atoms, this is the iodine, bromine, chlorine, thiol, fluoride, ester, ether, alcohol, nitro groups, amide, dialkyl secondary amine, and amine, carbon tetrachloride, and this is the derivative of ester. So lowest priority is the hydrogen and deuterium. So you should also keep in mind by assigning the configurations. Consider the following examples and specify the configuration R or S notation. For example, 1,1 chlorobromoethanes. Now go to the steps 1. Determine the priority of the groups attached to the chiral carbon atom. The priority order is Br greater than Cl, CH3, NH. Then step 2. Position the lowest priority group down away from the observer. This is done by interchanging group bonded to asymmetric carbon. Remember that interchanging any pair of group in a Fissure projection invert the configuration. Interchanging two pair of groups retain the original configuration. Thus the interchange operation must always be done in pair to avoid the configuration change. So this is the order 1, 2, and this is the 3 and 4 to exchange this with the bromine with the CH3 and hydrogen with the Cl2. Then specify the direction of decreasing priority of the 3 groups like 1, 2, 3. Ignore the lowest priority groups, that is hydrogen. If the group 1 and 2 and 3 are arranged in a clockwise fashion, the configuration is R. If the group occurs in anti-clockwise fashion, the configuration is S. This is not the actual method, but you will try with these tools. The above example configuration is yes because group 1 and 2 and 3 are arranged in anti-clockwise fashion. So configuration of compound with more than one chiral center. The configuration of compound with more than one chiral center can also be specified by the RS system. The configuration of each chiral carbon is determined individually using the same rules as for compound with one chiral center. So this is the both carbon 2 and carbon 3 are chiral. So configuration for carbon 2, you can see look at this carbon where you want to give the configurations and accordingly give the priority. Now order of priority is you have the OH, you have the aldehyde, you have the dialcohol and you have hydrogen. So configuration at C2 is 2R. So configuration for carbon 3, again you can repeat the same way. Order of priority is OH greater than CHOOH and CH2OH and hydrogen. So configuration at carbon 3 is 3R. So name of compound is 2R and 3R. Now 2 represent the position and R represent the configuration. So 2R, 3R, 2,3 trihydroxybutanol. So look at these examples. R configuration of lactic acid and plus means S configuration of lactic acid. So look at the negative lactic for an examples how to assign configuration sequence. Rule 1 says that OH is ranked 1 and H is ranked 4, but it doesn't allow us to distinguish between methyl and COOH group because both groups have a carbon in their first atom. Now sequence rules 2, however, says that the C double bond OH rank higher than CH3 because O the highest second order atom in C double bond OH outrank H. The highest second order atom is CH3. Now turn the molecule so that the fourth rank group is oriented towards the rear and away from the observer. Since the curve arrow from 1 OH to 2 C double bond OH to 3 CH3 is clockwise, right turn of the steering wheels, lactic acid has the R configuration. Applying the same procedure to positive lactic acid lead to the opposite assignment. Now you can see the optical isomers in cyclic compound. This is the cis form and this is the trans form. You know that this is a mirror image of cis superimposable mirror image, that is the meso compound. Non-superimposable mirror image, that is the enantiomers. So this is the cis isomers and this is the trans isomers. So optical isomers in nature, you know the positive limonene has the order of orange while the negative limonene has the order of lemon. So you can see the without any things you can easily distinguish with the color. Here is the orange and here is the yellow. So this limonene, racemic fluoxetine is an effective antidepressant, but it has no activity against migraines. The pure S isomers, however, work remarkably well in preventing migraines. So you can see the fluoxetine prevent migraines. It also contains, this is the chiral center, and these four are different group. So why do different isomers have different biological activity? To exert its biological action, a chiral molecule must fit into chiral receptor at a target site, much as the hand fit into a gloves. But just as a right hand can fit only into a right hand gloves, so a particular stereoisomers can fit only into a receptor having the proper complementary shape. Any other stereoisomers will be a misfit like a right hand in a left-handed gloves. So this is the pictorial diagram. These isomers fit here and this isomer do not. So my friends, I hope this is clear to you. If you like this video, then subscribe my channel, and thanks for watching.